All right, so we've talked about parametrization of curves. So we were given some sort of curve. So for example, y equals f of x. So this could be like the parabola 2x squared minus 3x plus 1. And we're able to parametrize it by letting x equal t and y equal the function by plugging in the t. And a lot of these things, all of these different types of curves, we were able to do a lot of cool things with them. So for one, we were able to find scalar line integrals. Okay, so line integrals are for scalar fields. Line integrals over scalar fields. Okay, and that was basically the integral over c f of x comma y ds. So we were able to find that, and if we know that f of x comma y is like a density function, then basically this is calculating the mass of this particular curve or a wire that follows this particular function. So either circle, ellipse, line segments, some sort of parabola or whatever. We also looked at line integrals over vector fields. And that looked more like integral over c of f dot dr, which also is the same thing as integral from a to b of plugging in r of t into the force field and then dotting it with the derivative of it. Okay, so we've kind of looked at this thing, which is basically the amount of work done. So if you have some sort of field and you got some sort of parametric curve as some sort of path, you are able to calculate the total amount of work there. And in addition to that, we saw that this formula can be pretty crazy, especially when you need to parametrize this curve. And the parametrization involves a lot like the magnitude, and especially when you're dealing with this scalar field. So we found a couple of alternatives. Some of the alternatives were using the fundamental theorem of line integrals, which basically meant that if you can find a potential function, if you have a vector field that's conservative, you can find a potential function and then just plug in the endpoints. So regardless of whatever the parametrization was, you can still find the total amount of work by just looking at these endpoints. And we also said that if something's not conservative, but we know that this particular field is, this particular curve is closed, we can use Green's theorem to kind of figure out what that is. So here is the parametrization of curves, and we did a lot of stuff with line integrals. Now what we're going to do is we're going to talk about parametrization of surfaces. So we were just looking at curves. So here's x, y, and z. Right? Oh, not that. X and y. We had a curve, so maybe along this. And we were looking at this path, and we were able to find the total amount of work. Okay, done. Given some sort of field. So whatever this field looks like. So we were looking at curves. Now we're going to look at surfaces. So remember, I was saying that line integrals, sometimes are called curve integrals. Now we're going to look at surfaces. So now we're going to extend this idea of line integrals, but now we're going to do it with a surface. So now instead of a curve, we got some sort of surface. And one of the first things that we got to make sure that we do before we start doing surface integrals is be able to parametrize some surfaces. So now we are no longer in 2D, now we're in 3D, so we got a function of two variables. So now here is a really quick and easy way to parametrize a couple things. So to parametrize a function of x and y, it's pretty easy. Just let x equal x, y equal y, and z equal f of x comma y. You could also let x equal u, y equal v, and z equals f of u or v, right? So before, here our parameter before was t. Here you can just, all you're gonna need, so let me actually do that. That's actually really important. So here we only have one parameter. And that one parameter was t. Here you're gonna have two parameters. And those parameters can be x and y. You can let x and y, or you can let them be u and v, or you can let them be theta and r. I don't know, whatever you can simply think of, whatever variables you want. So to parametrize a surface is very easy. Let x equal x, y equal y, and z be the function of the two variables. Cylinders, you'll see this is just cylindrical coordinates. Let x equal r cosine theta, y equal r sine theta, and z equals z. So this is just basically cylindrical coordinates. So whenever you want to parametrize a cylinder, this is how you would be doing it. Cones, you can use the first parametrization, of course. You can just let x equal x, y equal y, and z equal the square root of all this stuff. Or you can just convert also to polar. But z here is AR, where A will be how much is the factor, the stretching factor. So you do have this extra A, and then multiplying by the radius R. Paraboloid, same thing. Sometimes you can use the same parametrization, or you can use polar. X equals r cosine theta, y equals r sine theta, and z equals AR squared. In a sphere, basically spherical coordinates. So here are just some of the basics. So let's just do a couple of examples. So before we get to it, so let's say we want to parametrize, I don't know, maybe some plane. Let's say parametrize. So convert it to parametric equations. So let's say you want to parametrize z equals x plus y. So all we really got to do is now, if you think about it, the parametric equations you had, when you had one variable, you had two parametric equations. When now you have a function of two variables, you're going to have three parametric equations. So you're going to have three of them. So we can literally just let x equals x, y equal y, and z just equal x plus y. So we can just do that. You can also let x equal u, y equal v, and z is just equal to u plus v. Okay, so typically if you wanted to make it into a vector function, right, if an r of u and v, instead of r of t, now we have r of u and v, you could just make it as x, comma y, u, comma v, comma u plus v. So this would be a way to parametrize something like that. Now let's say we wanted to do something else. So let's say we want to parametrize, let's say we wanted to do, I don't know, x equals 5y squared plus 2z squared minus 10. Okay, so now notice here we have a function of x. So we have x is equal to a function of y and z. So we can let y equal y, z equals z, and then just let x equal y, 5y squared plus 2z squared minus 10. Okay, so basically our function, you can write it rxy, or r of uv, is just going to be 5y squared plus 2z squared minus 10, y and z. Okay, so that's something that we can do. Alternatively, because this is a paraboloid, you can also use this other parametrization. Okay, so letting x, you will let y equal r sine theta, z equal r cosine theta, and then just plug those guys in there as well. So you can do that also. Okay, typically you want to make it as easy as possible. Okay, let's do another one. So let's say you wanted to parametrize. Let's say you wanted to do the sphere maybe. X squared plus y squared plus z squared equals 9. So you can easily have it as x equals x, y equals y, and then z equals to the square root of 9 minus x squared minus y squared. Okay. So you can definitely do something like that. And let's say we were just looking at the top half of the sphere, then you could easily have x comma y comma square root of 9 minus x squared minus y squared. So you could do that. Now, one of the problems with this is that you have square roots, and sometimes when we do integrals, the square roots can be kind of ugly. So you can definitely do parametrize a function like that, but I think it'll be better to just do it in spherical coordinates. So I'm just going to do spherical so you can see that rho in this case is equal to 3. Theta in this case would equal to 2. Oh, well, theta is just going to be theta, right? So we're going to get theta is going to be theta, and phi is just going to be phi, because phi and theta are going to change, but we know that the radius is always going to be the same, 3. So we can just make our parametrization using these guys. So we can just say 3 cosine theta, sine phi, then 3 sine theta, sine phi, and then 3 cosine phi. So this is another way to parametrize. And this might actually be a little bit better than this guy because this one is a lot easier to work with. Okay, so there's not one unique parametrization. If you ever are lost, you can always just use the very first one, but the other ones are also good as well. Notice that this green one, I could have easily just used the paraboloid one, or I could have used the first parametrization. Okay.